Thank you very much. So I promised you this morning to talk a little bit about the numerical results we obtained. Let me jump right in. So what we do is we simulate the flow with a so-called Lattice Boltzmann method. It's a method, a gas kinetic approach for the simulation of weakly compressible flows. And basically what we do, we solve the so-called lattice BGK equation for the density, pressure, and momentum, as you see up here. And basically this describes a relaxation towards the thermodynamic equilibrium. And since this is weakly compressible, you have a decoupling of the energy equation from the rest of the Navier-Stokes equations. And then you need to simulate the temperature individually. And we do this by another approach, by adding a second equation here for scalar transport of the temperature. Okay. This is all what I will show on the equation. So basically we had a look at three different nasal cavities, as you see here, and we had an evaluation by rhinologists and also with an RSBI from the patients. And basically what you see here is that we had a classification poor, fair, and good, and we wanted to try to match with the numerical simulations if we could say something similar with the variables we're looking at for these nasal cavities. Yeah, so we did an extraction of the nasal cavities about the mesh generation I talked this morning, and what you see here is the flow distribution. Basically, you have here on the for the poor case, there was actually a person who underwent surgery. You see there's a missing center turbinate on the left side and a wide opening to the paranasal sinus, and missing lower turbinate and a septum perforation on the right side. And then in the center, the fair geometry, you have a strong swollen center turbinate and lower turbinate on the right side, strong septum deviation and niche-like regions. And for this one that we call good, like a slightly swollen left nasal cavity. So we simulated with these Reynolds numbers, which are shown there, which are based on the hydraulic diameter of the pharynx with 360 milliliters per second, and for the temperature at the inflow we used 20 degrees Celsius and 30 degrees Celsius at the tissue surface. So we had a look at the pressure loss along certain streamlines that went through the center of the nasal cavity, as shown exemplarily here for one of the nasal cavities. And on the left upper side, you see juxtaposition of those for the, let me see, for the left cavity and for the right cavity. And here, maybe, can I? Maybe have the microphone. So what you can see here, this one with a strong pressure loss is the one with a very swollen turbinates. While the others here, the good configuration and which we call the poor configuration, which was pretty open, didn't have that problem. Yeah, so here on the right side, I will show something like a evaluation from our side, so plus minus. Okay, so then we had a look at the temperature distribution, and what you basically see here is that with the good configuration and with the medium configuration, the patient or simulation showed that we can almost heat up the temperature up to body temperature in these configurations, and that one with the operated surgery, with the surgery nasal cavity, is only able to heat up the temperature up to 31.5 degrees Celsius. Yeah, so from this point of view, we also have an evaluation here on the right side. The good configuration and fair configuration performed very well, while the poor configuration was doing not so good. Then we also had a look at the wall shield stress distribution, which may cause inflammations. These are the wall shield stresses plotted on the nasal cavity surfaces, as you see here, and obviously this nasal cavity here, with which was a very stuffed nose, has a very high distributions everywhere. So we had a look at the local maximum wall shield stress distribution. So here for this poor nasal cavity, we see we have very high local maxima, which actually appear here in this region and down here. And for the surface average one, the medium configuration at the highest, which you obviously can also tell from the picture here. So we have a twofold evaluation here, and as you can see here, the lowest one is actually this one, the good configuration. So this is why we have plus here. Then we also had a look at flow regimes. For example, we investigated the nasal cavity, which was pretty stuffed. So we saw that there were some fluctuating structures appearing in the pharynx, so we had a detailed look at that. So basically, this is the pharynx region, so you're looking from this direction onto the pharynx. Yeah? So this is a flow field development, left cavity, right cavity. And basically, we had a look at correlations, 2-point correlations from point P4, what you see up here, coming from the left side down here to P0, 1, and 2, and P3. And just a juxtaposition of the results that we have, you have here on the left side from P0 to P3, this correlation, you see that there's not much influence coming from the right side, while on the other side, from here from the left side, you have a very strong correlation. Then, furthermore, we also have a look at eddy turnaround times. So what you basically do is a correlation in a single point, and match you have a time series and pass the time series across this and do the correlation. And what you actually see here that for points P2 and P3, yeah, which are 2 and 3, you have a very long eddy turnaround time. Yeah, and then for here, this one P1. Yeah, this is the important one. You have very small turnaround times. You have like fast rotating vortices. And then we also had a look at the energy spectra here. This is this picture for the different points. And you also see then here, for example, this is here P1, the green one, which you see here on the very top, contains the most energetic flow. The pictures down here, this is more like for visual understanding. You see again here, like that you have an energy generating region here on the left side, and then the vortices are transported downwards. And this is an instantaneous picture, so this is time average here. Okay, to summarize, yeah, so we had a look at 3 different configurations, and actually these the investigations we did with the simulations actually matched the questions to the patients and to the rhinologists pretty good. For the good configuration, we had a low pressure loss, easy respiration, good heating capability, good preparation for the lung, of course, and lowest average and local wall shear stress. So maybe a low risk of inflammation for the fair configuration. The highest pressure loss, yeah, that was the one which was pretty stuffed. That means strenuous respiration, of course, although we had the best heating capability in this case because the flow was transported very close to the surface, and then the medium local wall shear stress was medium. Then for the poor configuration, obviously because we had removed parts of the nasal cavity, we had a low pressure loss, meaning easy respiration, although then we had a lowest heating capability, increased risk, for example, for lung pathologies, and then the highest local wall shear stress for this case. So what I think is we need to consider a mixture of all these parameters, not a single parameter, but we have to look at several parameters and combine them somehow to find an evaluation of a nasal cavity. Thank you very much.
Your Reynolds number is pretty low, right?
It's the Reynolds number that corresponds to the volume flux. So we had a look at normal respiration, yeah, 360 milliliters per second at the pharynx, and it stays on the pharynx depending on what you think where the Reynolds number.
Yeah, but the other question is, if you want to increase your Reynolds number, because Lattice Boltzmann is escalating so bad.
Yeah, you have different options. You have different options. Then you could go to MRT method, for example, yeah, or what else here? You have different that's Boltzmann sweeps to stabilize this. Yeah? Yeah.
Okay, thank you.
Yeah. So if you have simply use the BGK, of course, that worked in this case. But if you consider simulating a sniff, for example, you may need to switch to another method, Lattice Boltzmann method.
Yeah.